Welcome to an online module of NRS 375. In this module that is split in 4 short parts, we are going to see how we perform positioning using a satellite navigation system. So we finally answer the question of how we are going to know where we are using GPS and all of the equivalent non-US systems. This is an operation that by now we take for granted, but let's keep in mind that until just a few decades ago, this was the domain of science fiction. So I'd like to start with this module with a little tribute to Star Trek. If I think about all the cheesy stuff that was in the original show, the GPS and cell phones is one area where we really got to a point that was quite unthinkable a few decades ago. In this first part of the module, we will do a very quick survey of what it meant to do positioning before the advent of GPS. So if we don't have a cell phone in our pocket and we don't have a GPS receiver and we want to use a map, we need to know two things. First of all, how to orient the map, how to point to the north. And then we need to know where we are. We need to know fundamentally our latitude and longitude. To know the north is pretty straightforward. We've seen that in one of the modules at the beginning of the class when we talked about compass and magnetic declination. So fundamentally, if you have a USGS topographic map, it will report the magnetic declination, and then you will get a compass out of your pocket, look at the direction pointed by the north arrow of the compass, corrected by the magnetic declination, and you know how to point your map to the true geographic north. Latitude and longitude are quite a bit tricky. In particular, latitude is tricky, longitude is extremely tricky. The latitude can be calculated doing solar observations at noon or observing the elevation of the Polaris at night. Position of the sun can be predicted with high accuracy as a function of our latitude, day of the year, time of the day. As a matter of fact, you have all encountered at some point a simple traditional device that uses this property of repeatability of the position of the sun. The sundial is a simple device that tells us the time of the day based on the position of the sun in the sky above us. Sundials are site-specific. If I build a sundial that works in Moscow, Idaho, and I take it, let's say, to Florida, it is not going to work. This is because the position of the sun is a function of the latitude. Therefore, the position of these circles and lines on the sundial is also going to change as I build a sundial that works in different places. Alternatively, our problem in positioning is how to know our latitude. So in this case, we use a different device. We use a sextant. The sextant that has been on board pretty much every ship for centuries and was abandoned only recently is a trigonometric device that allows for a simple measurement of the elevation of the sun over the horizon. What do we do with it? Well, we always know at least once a day what time it is. We can always find the exact time of the solar noon, because it's the highest elevation of the sun over the horizon. So in the absence of any other device, we know the elevation, we can measure with the sextant the elevation of the sun at the highest point during the day. If you look at this chart, well, we know that the sun rays will hit us at an elevation, we call it delta, and that will change with the day of the year. Once you observe the angle between our local horizon and the position of the sun, we can, with a few trigonometric steps, derive our latitude, that little angle phi on the plot. Likewise, we can observe the elevation of the Polaris, and with very similar calculations, go back to our latitude. You can actually look in practice at how these calculations are done. We have one angle, the angle alpha, that we can measure. We are in point P, so angle alpha is the elevation of the sun over our local horizon, that thick line that touches the Earth on point P. The elevation of the sun relative to the equator, that's the angle delta on this plot, is known. We don't need to calculate that ourselves. Sailors haven't had to calculate that ourselves for a few centuries. That can be predicted, and it can be put in a table. So every ship used to have a nautical almanac on board where this value was tabulated. Once we have the value of the elevation of the sun for a given day of the year over the equator, and we have the observed elevation of the sun over our local horizon, then the latitude can be derived using a very simple calculation that exploits the basic property of the triangles. It exploits the fact that the angles of a triangle will add to 90 degrees. So here we have our little formula. Our latitude is going to be 90 plus delta minus alpha. Delta is tabulated, alpha is observed. As a result, I have my basic latitude. The longitude instead is complex to derive, and that's because, unlike the equator, the Greenwich meridian does not correspond to any physical property of the planet. It's just a convention. It took several centuries to determine with any accuracy the longitude at sea. There was a nice book a few years ago that was really made to the top of the bestsellers on the New York Times list. Longitude, the true story of a Longinus that solved the greatest scientific problem of his time. If you are fascinated by the problem, I really recommend reading this book. It's very pleasant. But we will end this module with a recommendation to watch a short documentary from the BBC series The History of the World in 100 Objects. That is pleasant to watch, nothing difficult, it's just a simple introductory level documentary that will give you an overview of how we got to measure time and linking that to longitude. We will restart the next module starting from here and taking for granted that as a reading you have watched the small documentary. Thank you.